Okay, so yes, good morning, everyone, to the United States, and good afternoon to our keynote speaker. I will shortly introduce Irene-Angelica Chounta to those who probably don't know her. Since 2021, she's a junior professor, the equivalent of assistant professor in computational methods in modeling and analysis of learning processes at the Department of Computer Science and Applied Cognitive Science at the University of Duisburg-Essen in Germany. She did a PhD in 2014 in the research group of Nikolaos Zavouris at the University of Patras in Greece, where she worked in the area of HCI, machine learning, and CSCL. From 2014 to 16, she was a postdoc researcher at Ulrich Hoppes Group in Duisburg, where she now is a junior professor, in the Collide Research Group, where she focused on learning analytics. This was or is also the group where I did my PhD in 2005. So we have a strong connection. 2016 to 2018, she worked as a postdoc research fellow at the Human-Computer Interaction Institute at Carnegie Mellon University, collaborated with Bruce McLaren and Sandra Katz, amongst others. And before she was appointed junior professor from 2018 to 2021, she was a senior researcher in Tartu, Estonia. It fills me with great pleasure that she's our keynote speaker today, and the title of her talk is Computational Methods for Modeling and Analysis of Learning, Opportunities and Challenges for Artificial Intelligence in Education and Learning Analytics. So please, the floor is yours.
Thank you so much, Andreas. Thank you for inviting me. It's really a huge pleasure to be here with you today. And in this talk, I will be exploring the use of artificial intelligence and learning analytics with the aim to support learning from the perspective of personalization and adaptation. And I will be relating it to computerized tutoring and scaffolding. I will discuss the theoretical and practical implications of computational analytics for monitoring and guiding complex human activities. And I will elaborate on why this is a great time to move towards models that facilitate seamless transitions between formal, informal, and impromptu learning. Finally, I will reflect on how we can bridge the gap between pedagogical theory and modern data-driven practice, while safeguarding learners' agency and autonomy that may be threatened from over-monitoring, over-scripting, and micromanaging. So usually what I like to do is show the map of all the places I've been around the world. And Andreas, thank you for the wonderful introduction. Like you already said, I returned back to the place where I did my first postdoc with Ulrich Hoppe, and that's a great pleasure to be in Duisburg-Essen. So here I lead the interdisciplinary research group, Computational Methods in Modeling and Analysis of Learning Processes, or in short, we call it COLLAPSE. And this is a funny title that we like to share around because although we are quite young and small group, we funded the group in 2021. We think that we're strong and we're not collapsing. Currently, we have 6 members, but we have big ambitions for changing the world. And we envision to do so by exploring the space between digital technologies and education. We are genuinely interested in how we can use modern technologies in order to facilitate and promote learning. So, for example, how we can use mobile devices to take advantage of geographical context, how we can use real-time collaborative systems to enable people working together from a distance, how we can support learners in acquiring skills such as critical thinking and problem solving, which are necessary competence for the digital age. However, what fascinates me personally the most about educational technologies is that at the end of the day, when the learning activity is over and we turn off the computer to go home, our digital trace does not disappear, but instead it is saved and it can be used at a later time to reconstruct the activity itself, to help us identify potential issues, bottlenecks, and even to pinpoint successful learning episodes so as to improve future practice. And even better, technology nowadays allows us to use these data traces to support students in real time by providing appropriate scaffolding and feedback when and where necessary. So eventually, this generalized consensus of using data-informed evidence to promote learning has led to the emergence of what we know now as learning analytics. And here I use the term learning analytics to define the human-centered design discipline that employs computational methods, such as artificial intelligence methods, to explore data traces in order to identify patterns that indicate learning and can be used to further promote it. Now, our research at the Collapse group focuses on using artificial intelligence methods in order to develop computational models of human cognition that will allow us to design personalized and immersive learning environments that adapt to student-specific needs. And to do so, we aim at combining different analytical methods of different natures, such as process-oriented methods, content-oriented methods, and network-oriented methods. And at the same time, also explore different contexts, such as individual learning with intelligent tutoring systems, collaborative learning, and learning by doing. Now, the core rationale is that learning is a complex human activity, and in order to model it, we have to synthesize information from different sources and with different granularity, and this is what we're doing with learning analytics and artificial intelligence. So from the perspective of our work as a research group, and while using examples from our work, I will attempt to tackle two opportunities for AI Ed and learning analytics, namely the use of computational models as pedagogical proxies and how to extend learning beyond the classroom walls. Consequently, I will also discuss two challenges, the new roles envisaged for teachers and how to safeguard autonomy and agency of stakeholders in technology-rich contexts. Now, one of the biggest criticisms of data-driven approaches is the lack of theoretical foundation and pedagogical grounding. The opportunity here is to design such computational models that can be used and act as proxies of good pedagogy. For example, if we could pinpoint what makes some students learn more or easier or faster than others, and we could model this behavior in a computational way, then we would also be able to provide support when needed. And here, to define the appropriate moment to provide support, I'm using the theoretical concept of the zone of proximal development. And for those who don't know, according to this theory, this is a theory of Lev Vygotsky, there is a cognitive area known as the zone of proximal development in which learning occurs. So in this sense, providing instruction and scaffolding is most beneficial when students are in their zone of proximal development. If a student is below their ZPD, then no matter what help they receive, then learning is not feasible. If the student is above their zone of proximal development, then practically they don't need additional instruction or help. The students can figure it out themselves. Now, teachers have the ability to evaluate the student's learning state dynamically, and by synthesizing various information sources, such as the students' comments, their responses to questions, their facial expressions and gestures, their prior performance experience they have with them, and so on. Therefore, teachers, I argue, are potentially able to assess when to provide support in order to get the desired response from students, and that's why they are so successful in their job. However, my question was whether we could get a computational model to do in real time what the teachers do when assessing students' learning state. And the challenge here is to model the zone of proximal development in such a way so as to be able to identify when a student is in this zone and accordingly provide instruction and scaffolding. To that end, I propose the combination of a theoretical and data-driven approach that aims to operationalize the zone of proximal development using machine learning on students' data when they practice with learning tasks. And I used as input data about the student's background knowledge and trained the student model as a binary classifier that practically predicts whether a student will be able to carry out an upcoming learning task correctly or not based on the student's prior practice. Here, to operationalize the zone of proximal development, I propose the concept of the gray area that you see on the left side of the screen. And this is the area in which the student model predictive accuracy is questionable. The rationale is that if the student model cannot predict with acceptable accuracy whether a student is able to carry out the learning task successfully, then this might very well indicate that the student is in their zone of proximal development, and therefore the outcome is kind of unknown or questionable. The research hypothesis is that this area, the gray area, expands around the classification threshold of the binary classifier, and consequently the area above the gray area signifies the cognitive state in which a student can carry out a learning task without any help. And the area under the gray area signifies the cognitive state in which a student will be unable to carry out a learning task even when they receive help. So first we tried out the gray area approach in intelligent tutoring systems, and that is computer systems that provide immediate and customized feedback to learners without the intervention of teachers. So specifically, we carried out this work during a collaborative research project between the University of Pittsburgh and Carnegie Mellon University with my colleagues there, Pamela Jordan, Sandra Katz, Patricia Albacete, and Bruce McLaren. And the aim of our project was to support high school students in learning conceptual physics by offering adaptive feedback using a natural language based tutoring system named REMAC. The approach was validated through extensive pilot studies, both offline and online, with approximately 400 participants in total. And indeed, the results of the pilot studies revealed that, on the one hand, the accuracy of the student model increases as we move away from the classification threshold, thus confirming our research hypothesis about the gray area. On the other hand, what we found out was that students who practiced using the student model learn significantly faster than the students who are not guided by the student model, right? So we had two conditions: the experimental condition. In the experimental condition, the students were using the model. In the control condition, the students were not using support from the student model. And indeed, in the experimental condition, students learned faster. Now, this finding was confirmed for students of both high and low knowledge background, suggesting that knowledge background here does not play a role in how fast students will learn. The other thing I would like to point out here is that we did not find that students in one condition learned more, right? In both conditions, students learned the same. Because the content was the same, so the learning objective was the same. However, in the experimental condition, they learned faster, meaning that they were able to move faster through the materials they had to learn. Then we explored the generalizability of the gray area by applying it over four publicly available data sets from STEM courses that were also facilitated with intelligent tutoring systems. And additionally here, we proposed a set of metrics for assessing the effectiveness of the gray area as a proxy of the zone of proximal development. Now, these metrics aim to capture sequences of hints and subsequent student responses. So when a student works with an intelligent tutoring system, they are able to ask for hints, and we were tracking these requests and also the student responses that were coming after the hint. Now, according to the theory of the zone of proximal development, a student is more likely to provide the correct response after receiving help and when they are in their zone of proximal development, because help is then beneficial for them. Therefore, what we did is we practically recorded and counted sequences of hints and correct responses, as well as sequences of hints and incorrect responses in and outside the gray area. So the results confirmed that in 3 out of 4 cases that we studied, students indeed provided more correct responses above the zone of proximal development than below, and vice versa regarding incorrect responses. So more incorrect responses below the gray area, below the zone of the gray area than above. This indeed confirms the original picture we had from the studies in Pittsburgh. And the thing that was interesting for us was that for one data set, this was not the case. So one data set was the exception in our, let's say, rule. After examining the different cases and contradicting them, we noticed that one factor that was different in the case that our hypothesis was not confirmed was the age of learners, who were considerably younger than in the other scenarios. Now, this might suggest that either the younger learners have different attitude towards learning and achievement, and this attitude does not discourage them from trying even when they're not sure about the outcome. So even though they might be below their zone of proximal development, they would still try and potentially get some tasks done correctly. Or the zone of proximal development of students changes in terms of size, depending on the age of the learner, which is something that we did not take into account when modeling the gray area. Of course, this has the implication that the gray area cannot be of a fixed size, but it should vary depending for once regarding the age of the learners. Now, regarding the sequences of hints and student responses, descriptive results confirm that students generally used more hints below the gray area than within the gray area. And furthermore, students solved more problems correctly within the gray area than they did below. Above the gray area, nearly no hints were used, but in most data sets, the majority of answers are correct. So these results align with the concept of the zone of proximal development, as students within the zone are assumed to be able to answer questions correctly when they get appropriate assistance. And in the case students needed a hint for answering a question within the gray area, the subsequent answer was more often correct than if a hint was used in order to answer a question below the gray area. So we saw this difference in the effectiveness of hints. Below the gray area, students more often asked for another hint in order to answer the question, and that led to sequences of hints one after the other until the system was giving them the right answer. Now, what is important to note here is that in most cases, in most comparisons, the results were not statistically significant, but we think that this happened because hints were rare. So less than 5% of the total responses were hints. And that means that the students did not ask for help, even if they needed it. And this is indeed consistent with findings of previous studies about the usage of hints in intelligent tutoring systems, and is referred to as hint refusal, and it implies that students rather tend to guess instead of using hints. Now that led us to think, what if we had a way to use time as a feature when modeling cognitive and knowledge state? And then we could give hints to students when we judged that they needed them, but without the students having to ask. Or alternatively, stop students from receiving hints when we think that they don't need them. Now, in particular, we're interested in exploring the relationship between response time of students and student performance. And our hypothesis is that students who reply either too fast or too slow, they are more likely to provide an incorrect answer. If students tend to reply too fast, that may mean that they don't take the time to read the question or the task appropriately and to retrieve knowledge from their memory. If the students take too much time to respond, then this might indicate that simply the students don't have the background knowledge that is necessary in order to answer the task. So in other words, what we're saying is that there is a temporal area that is different for each student and in which the student is more likely to answer correctly. Now, our earlier research suggests that on the one hand, this hypothesis is confirmed for STEM-related courses, and on the other hand, the relationship between response time and student performance is not linear. And this is important because many modeling approaches that tend to use time as a modeling feature for student performance, this is what they were assuming. Furthermore, we explored the impact of using response time as a predictor for student performance. And we compared the performance of models when modeling time as a linear parameter when modeling time as a quadratic parameter and when not using time at all as a feature. So the results showed that including response time as a quadratic parameter rather than a linear may improve the model's performance significantly, thus leading us to believe that most probably the relationship between response time and student performance follows some kind of a quadratic distribution. Now, based on these insights, we developed a time-sensitive tutoring system that provided hints based on the assessment of a student model and in combination with the time that elapsed from the time the student was given a task. So that is what we count as response time. We carried out a study with two conditions, a control condition where students received no hints whatsoever, and an experimental condition where students received time-sensitive support. And the results suggested that the students in the experimental condition, so the students who received time-sensitive support, performed better than the students in the control condition in terms of correctness. We followed up with a survey that practically we asked students about their experience with our time-sensitive tutoring system, and we saw that students rated the time-sensitive tutor higher on aspects such as efficiency, clarity, and ease of use. And the time-based tutor was scored lower only in one dimension, and that was the dimension regarding obstructiveness. So what we think that happened was that the students perceived the pop-up hints as nuisance. So the hints that they were receiving without them asking, for them, it was an annoyance, this sudden appearance. This practically shows that user experiences and usability, you should never turn your back on them. In January 2023, we started working on Horizon Research and Innovation action project called Augmentor that aims to develop a novel pedagogical framework that promotes both basic skills and what we call 21st century competencies by integrating emerging technologies. And the idea is that we combined all the research I showed you up to here in order to support students and teachers who carry out learning activities with the use of technology through an open access AI boosted toolkit. So augmented intelligence, we chose the term augmented intelligence here because we want to emphasize that we want to help humans rather than replacing them. So apart from formal learning within the classroom or as part of some formal learning configuration, learning also happens, let's say, out there. So in particular, we are interested in the potential of events like hackathons or makerspaces as impromptu learning opportunities. And such events share many characteristics with project-based learning, including a focus on practical problem-solving activities, an emphasis on collaboration, creativity, and so on. So an interesting characteristic of project-based learning is that the learning process and the final outcome cannot be fully predetermined, which is what practically happens in events like hackathons. So although not primarily devoted to learning, hackathons and similar events rely on similar principles, and we envision that this can be an opportunity to define new types of project-oriented learning in technology-rich contexts. And to situate modern educational approaches using hackathons as learning opportunities, it is helpful to identify best practices and approaches for incorporating educational objectives into these events. For example, organizers could provide resources and guidance using specific tools, or it might be additionally useful to explore how these events can be integrated into formal educational programs. Now, although hackathons have been advertised and communicated as a way to promote learning, a recent literature review we carried out demonstrated that even for events that state learning as an explicit and direct objective, there is a lack of defining learning goals, there is a lack of learning designs to guide the activity, and a lack of robust assessment of learning. So practically that means that we might want to have a hackathon that promotes learning, for example, learning programming or some similar practical skill, but we just go there and we expect learning to happen. And we know better than that. We know that this is not the case. At the same time, despite the importance of standardization, systematization, and evaluation of knowledge, we acknowledge that introducing rigorous and robust structures to support learning in such events might affect their fun, informal, and spontaneous character, and potentially might have a negative effect in participants' motivation for attending. And in this line of research, our aim is to explore how we can use AI and learning analytics to study the communication patterns of hackathon participants during the course of an event, to identify what characteristics of hackathon project or hackathon teams promote project continuation after the event is over, and to even analyze the artifacts produced during a hackathon. That may be a piece of code, a tangible artifact, something that somebody created in a workshop, or even a sequence of text messages as evidence of learning. Now, at this point in time, we do have the technical capabilities and capacity to synthesize information about students of different types and different granularities and on various levels in order to sustain holistic representation of student state. So not only on the cognitive level, but also in relation to other aspects of human nature, such as social skills and personal traits. In this sense, the student representations we acquire from cognitive models, as we know them, they can evolve into a computational system or computational systems of human cognition. And this means that the student model moves away from a monolithic construct and instead it transforms into a multifaceted system where each facet interacts and informs the others, contributing to the biggest picture puzzle. So in other words, we see different computational models as puzzle pieces that in the end we put them all together and they will give us the greater picture about a learner. Now, the impact of designing a personal computational system of human cognition like that could consequently be twofold. On the one hand, it could bring us one step closer to personalized learning environments by guiding automated online tutoring systems that would be able to provide feedback according to students' needs without the intervention of human tutors, for example. And this system would be directly updated, taking into account the student's performance, affect, and overall state. And based on this multiple perspective, it would adapt the goals, instruction, and feedback. On the other hand, and provided that a system like that can be maintained over time for a single individual, it could document important information about the process of this individual, and thus it can practically serve as a digital portfolio of a learner's evolution over time in terms of competencies and skills that can be potentially shared and communicated when needed. So, for example, you can go tomorrow to your future employer and show your digital portfolio that is with you and accompanies you from day one of primary school until you finished your university, your undergrad or master degree. At the same time, this system can potentially contribute to expanding learning beyond the classroom and the school time in a seamless way. So learners can potentially connect their own devices to track their activity, like their smartwatches, and to integrate their extracurricular activities to document these impromptu learning opportunities. And with this last point of seamless transition and constant monitoring, I would like to move forward to the open challenges for AI and learning analytics. Now, I admit that what I described as the future of learning, my ideal future of learning, one can argue that is data-driven dystopia instead, where all human activities are tracked, monitored, analyzed. All human activities are subject to optimization and constant comparison to some externally imposed golden standard. And one can argue that in such a setting, stakeholders' autonomy and agency is only virtual, if not absent altogether. Stakeholders' decisions and actions are imposed by some very sophisticated and complicated algorithm, let's say in the form of recommendations, and these recommendations may indeed be correct for example, a recommendation about a learning activity being appropriate for practicing a skill that the student is missing. But instead of providing more opportunities and options as we would like, we might actually in this way limit the opportunities and options by hiding the potentially wrong or not good enough, and thus preventing us to learn from our own imperfect decisions and our own mistakes. Now, I argue that one way to address this challenge is to involve stakeholders during the design and development process and creation of services and products that prioritize humans and their needs. Particularly regarding artificial intelligence in education and learning analytics, it is imperative to gather requirements and elicit needs from multiple stakeholders, such as teachers and learners, who are key in this context, but also more, let's say, peripheral roles, like, for example, parents. Now, consequently, the goal here is not to develop the best fitting model or to use the most cutting edge prediction algorithm, but instead to serve the stakeholders' needs and wishes, despite how trivial or non-exciting for us the task might sound. Now, in our recent work, we focused on the role and the perspective of teachers as stakeholders regarding artificial intelligence as a tool to support their practice. And specifically, we focused on Estonian teachers of K-12, so primary and elementary education. And one of the reasons for doing that was because Estonia is discussed as the digital innovation hub that has achieved to integrate ICT in most aspects of everyday life. The other reason was that I was located at the time in Estonia. To elicit challenges that teachers face, their needs and requirements, we borrowed the notion of superpowers as a suggestive metaphor for artificial intelligence, and we aim to answer two questions. How do K-12 teachers perceive artificial intelligence as a means to support teaching, and what are their expectations from artificial intelligence? And the second question was, what are the perceived challenges that K-12 teachers face regarding their work practices? So we surveyed 140 participants, aiming to gain insight into three aspects. The first aspect being teachers' perceptions, attitudes, and familiarity regarding AI. The second aspect being teachers' perceived challenges regarding their work practices. And the third aspect being teachers' profiles and work contexts. And that, of course, was reflected in the structure of the survey. So in the first part, we asked about participants' perceptions, attitudes, and familiarity with AI. In the second part, we followed up asking participants about perceived challenges. And here we wanted to capitalize on the implicit connection between AI and superpowers. So we asked teachers, if you could have any superpower that you wanted to help you do your job, what would the superpower be? And in the third part, we asked about participants' work practices, context, and demographics. So we saved for last the questions that did not require much cognitive effort. And the instrument that we used is available as part of the appendix of the publication in the journal of in the International Journal of Artificial Intelligence. Now, the majority of the teachers who participated in the survey, they stated that they have either limited or some knowledge regarding AI. So 4% of the teachers responded that they have never heard of AI before. And this was, again, in Estonia, that is considered a hub of digital innovation. And 6% of the teachers stated that they know a lot about artificial intelligence. So in order to validate teachers' perceived knowledge, we provided to the teachers statements related to AI, and we asked them to indicate which of the statements were true. And based on the correctness of their responses, we calculated a correctness ratio for each participant. So we did not find a statistically significant correlation between correctness ratio and participants' familiarity with AI. However, what we saw was that participants who rated their knowledge as passing provided more correct answers than the one who considered themselves as quite knowledgeable and even experts. Now, we argue that this can actually be a hindering factor when it comes to integrating AI systems in the classroom. Teachers who feel confident about their AI-related knowledge end up struggling due to false perceptions, and teachers who do not perceive themselves as knowledgeable, they refrain from using AI systems, although they do have the necessary skills. Then we asked the participants to list the positive and negative aspects of using AI in education. Concerning positive aspects, participants stated that AI could help them be creative in their practice. It would help them to group the student population in terms of knowledge state and in organizing the learning materials in terms of difficulty. Considering the negative aspects, participants raised concern with respect to the potential of hindering human communication, placing the human in the background, and also questioned the effectiveness of AI for tasks that require creativity and empathy. In other words, the participants were mostly concerned of AI as a replacement of the human. Now, moving to the second part of the survey, two researchers analyzed the participants' input to identify prominent topics referenced as superpowers in teacher responses. And overall, we identified 32 topics that we call them codes. The most referenced topic in participants' input was speed, and it was referenced 35 times, followed by personalization that was referenced 22 times. So it was clear that our teachers need more time. They think they need to be faster. The least referenced topic was assertiveness and reflection, each referenced one time, leading us to believe, to understand that teachers really don't need our help in order to self-reflect. They are perfectly capable of doing that on their own. So next, we wanted to identify underlying structures in participants' feedback. And in particular, we were interested in exploring whether the 32 topics that we identified from their input could be grouped in clusters that would reflect teachers' fundamental needs. And our analysis suggested 6 code classes, each class consisting of 2 to 10 codes. And these classes are effectiveness, efficiency, rapport, course preparation, personal attributes, and personal skills. So the first class relates to the efficacy or effectiveness of teaching in terms of instruction, and it is characterized by codes such as personalization and speed. Efficiency relates to the temporal aspects of teaching and time management, and it is evident by codes such as time control and multitasking. Rapport was prevalent in topics related to personal relationships, understanding, for example, empathy and reading thoughts. Course planning related to efficacy of teaching in terms of content preparation, and this theme is evident by codes such as content planning and finding materials. And here, we should also note that our participants pointed out that they perceive AI as a tool to help them find materials that are written in languages other than Estonian, their native language. The next the code class was personal attribute and skills. And these last two themes related to the abilities or qualities and skills that the teacher should acquire in order to be successful professionally. And these last two themes stand out with respect to the rest of the themes because they are teacher facing. So this means that they specifically point towards teachers and themselves rather than the teacher in relation to the learning objective or the teacher in relation to the classroom. To briefly discuss our findings, we saw that teachers demonstrated positive attitudes towards the use of AI in education, and they perceived it as a means to support them in retrieving learning materials, organizing lessons in terms of content and scheduling, and even reviewing homework assignments. And even though a common argument against AI integration in the workplace is that it will take over from humans and lead to job losses, this was a minor concern of Estonian K-12 teachers. On the contrary, participants pointed out their concern about the effort that it would require on their behalf to learn how to appropriately use AI technologies, and also potential trust issues that could arise from AI use. For example, some participants stated that they would not trust AI to carry out tasks without error, And most importantly, participants were critical about how AI could undermine human-to-human communication and hinder social aspects of learning, while they pointed out that they could see AI as a help to administrative tasks that would free time for them to do what they love, because teachers love to teach. Teachers also voiced their need for support in their own professional development skills, and that they would like to have in order to perform in technology-rich, clever environments. So, contrary to our expectations, teachers prioritized procedural skills that they perceived as necessary for their profession. For example, programming, analytical skills, or even foreign language skills. Now, this finding may suggest that the skill set required for teaching is changing to accommodate the needs of an IT-enhanced, data-literate society, and it might serve as a suggestion for developing new standards for teaching qualifications. We argue that by integrating an AI system in the classroom, we also give teachers new and creative roles that might not have been possible before the use of technology. For these new creative roles, teachers should be equipped with new skill sets. And it was evident from this work that even though AI is a well-discussed topic, there is the need for further contextualized and conceptualized discussions with stakeholders if we aim to develop AI tools that will find their way in the classroom. Most importantly, we should communicate how the technology addresses the stakeholders' needs and does not obstruct or hinder what the stakeholder perceives as important. And again, this might not be the same thing as what we perceive as important. By we, I mean as researchers. At the same time, considering AI as the solution to all educational problems might have detrimental effects, especially in terms of fair and ethical AI. This way of thinking could set us apart from AI itself and the responsibility its use entails. We envision as critical to establish cooperation between humans and technology, including AI, which may turn out to be a way more powerful strategy than the blind reliance on computation alone. So last but not least, I would like to discuss the role and importance of faith of artificial intelligence in education. And by faith here, I refer to the acronym that stands for Fairness, Accountability, Transparency, and Ethics. In 2022, we published a report for the Council of Europe with my colleagues Wayne Holmes, Jen Persson, Vanya Dimitrova, and Barbara Wasson that aimed to offer a critical view of artificial intelligence and education from the perspective of the fundamental values of the Council of Europe. And specifically, these values are human rights, democracy, and the rule of law. So this report includes broad connections between AI and education, and in particular, it focuses on three perspectives: using AI systems in education, using AI to learn about learning, and also AI literacy. Additionally, it focuses on the adoption of AI and the impact it will have on education. And it was designed, so we designed it to initiate the conversation and point at issues rather than provide a summary of the state of the art. And that's why it might be perceived as a bit more critical than one would expect, especially from computer scientists. So this report is publicly available via the Council of Europe, so please feel free to download if you want to read more about it, and I will be more than happy to hear your thoughts. Following the report, we communicated a survey to the 46 member states of the Council of Europe with the aim to document their current state regarding artificial intelligence and education. So we were looking for regulations and policies they have in place, what kind of AI-enhanced systems they use, for what purpose, what current practices they follow regarding learning with, learning about, and preparing to live with AI. And out of 46 member states, 25 responded, and some first insights were communicated during the AI Ed working conference that was organized in Strasbourg, by the Council of Europe in November 2022. Currently, we are in the process of publishing the report of the survey. So if you're interested to know more about this work, please do not hesitate to contact me. And I have put together some insights from the report and the survey that I would like to share as a takeaway message. So it looks like there is the need for rigorous, robust evidence from wide contexts regarding the use of AI in education in terms of scale, in terms of duration, but also in terms of geographical context. Currently, there seems to be a lot of hype that is not backed up by rigorous evidence. It is imperative to establish policies and regulations on local, national, and international levels to guide the integration of AI in education. What we have seen so far is that either such regulations and policies are work in progress, or that education falls under general guidelines for AI, or they don't exist at all. We think that this is problematic due to the impact the use of artificial intelligence may have on the development of young individuals, and consequently on education and the future of society as a whole. And here we want to reference the very rigorous guidelines that we have in medical research. Curricula for AI literacy are necessary for all levels of education in order to prepare the society for living with AI. And taking the recent events around ChatGPT as an example, we argue that AI literacy is an important skill that all people should acquire, regardless their level of education, background, current status, in order to be able to navigate safely everyday tasks. We need school and lifelong learning curricula that address both the human and the technological dimensions of AI, and that in order to ensure that everyone understands how AI works, but also what is the potential impact on our lives. Finally, in order to safeguard stakeholders' autonomy and agency, AI in education should prioritize and facilitate human rights, democracy, and the rule of law. And one way to do so is to strive for multidisciplinary approaches, bringing together educators, learners, parents, learning scientists and philosopher, computer scientists, AI engineers, commercial developers, and governments. Which leaves the question, why should we care now? Well, artificial intelligence in education is hardly a new topic, and learning analytics, it has some years on its back as well. So AI ed particularly is rooted back in the 50s, and throughout the past 70 years, it had its ups and downs. And in the US, research in AI ed is carried mostly in the form of intelligent tutoring systems. The rest of the world followed more socio-constructivist approaches. However, things seem that have started to change and to shift. So technological developments provide ample capabilities. In other words, the technology now is way ahead of the application, and we can proceed with minimum technical constraints to realize the dream. The effectiveness of current intelligent tutoring system has already caught up with human tutors, meaning that the challenge now is how to build tutoring systems that can do even better than human tutors. And political and financial organizations are taking the next big step regarding AI. National governments boost the agenda for promoting personalized learning and online learning. They invest in IT and prioritize online personal learning as a tool to acquire digital competencies and 21st century skills. Big tech companies such as Google, Microsoft invest in their AI and machine learning solutions for AI augmented education. And according to predictions, AI adoption in education will explode over the next few years and is expected to reach its peak by 2025. So my personal view is that in a time like this, where virtually everyone seems to have reinvented artificial intelligence in education and learning analytics, it is our responsibility and also opportunity as researchers working on advanced learning technologies to tackle such challenges and shape the future of data-driven learning on rigorous research principles and ethics. And with this message, I would like to conclude my talk and invite questions and comments. Thank you.
Yes, thank you very much. I think this was really, really interesting. And I guess that we have a few questions. I already see hands going up in the virtual world, but also I think there will be questions in the audience. Rita, I can't see hands going up in the lecture hall, but I would suggest that I probably just start with someone from the from Teams, and then we probably take turns. One online, one in present, if that's okay. There is a question from Hassan. Oh, sorry, I can't see the full name here because Hassan Abu. I can't see the rest of the name here. So sorry about that. But please.
No worries. Thank you very much for the very much interesting presentation and the really deep insights into the connections between pedagogy and technology, which is something that we honestly need more and more researchers to focus on. So thanks a lot for the insights and for the presentation. I have a point about the stakeholder consideration. The slide you have showed about all the stakeholders, including the parents, not only the learners and the teachers, including policymakers, is essentially a need that we feel working in this field, because I come from a teaching background and I'm currently working on computer science, and we feel the gap between the two domains that unfortunately is mostly controlled by the computer science domain. So from the technical perspective, we see more agency on developing those tools, and the teachers mostly rely on utilizing whatever exists, even if that happens in a research setting. So there is a need, I guess, for policymakers that can really push both domains towards each other, and not only teachers to learn about technology, but rather also technical backgrounds or technological people to learn about pedagogy and how to implement. My question is simply, how do you see this balance within the extremely fast development of technology, which is not accompanied by the same speed of development in teacher skill set enhancement, overcoming the AI illiteracy, and also the very slow development of policy making, even in on let's say advanced levels like Estonia, for example. There is still a large gap in speed between the technological development and the policy making, and that leaves teachers mostly behind the developers in terms of controlling the tools that are used in education. What can be then the solution to overcome this gap?
Great, thank you very much. I think you made some excellent points. Indeed, there seems to be this gap in communication between stakeholders, more prominently being computer scientists and teachers, although I will argue that from the computer scientist side, they would feel that teachers have a bigger saying in this debate, right? So, it depends, I guess, also a bit on what side you're sitting on and what is the general trend. I think the first and most important thing is to establish a common ground, right? Sit all together around the table and discuss what is it that we ask from education and what is that we aim for. And that was my point about different stakeholders putting first their own dreams and their own research interests than what we actually need. So I guess if you're crazy about deep learning, you will try to apply deep learning algorithms because this is what interests you, right? So if you have your favorite hammer, everything looks like a nail. And I think that this is a first step to practically sit all together and share a vision. what is that we want our education to look like in 10 years, in 20 years. And then based on this common vision and on our common values that we must also share, design a plan how to achieve this. I think you're right that policymakers should step up here and establish these regulations that we are currently missing, because it seems like because technology is faster, it seems like it's taking over. And in order to navigate to in a safe space, we need regulations. I would say that first, maybe establish regulation to make sure, that we don't have a negative impact from the use of technology, AI, but also technology overall, right, on education. And while we do that, also sit together and really set up a plan on how do we want the world to look like in 20 years, again, establishing also a common understanding of our shared values.
Thank you very much.
Okay.
Thank you.
Okay, so Rita, are there any questions in the lecture hall?
Anyone has any question? Yes, Dimitri. Yeah, I think that.
So, Irene, congratulations for your presentation. I really enjoyed, and congratulations for your work. It's a very thorough and deep investigation, starting from Patra all the way to Germany nowadays, but probably traveling the whole world. So one point I would like to share with you and probably have your comment is, I liked that you're studying in Estonia, and I noticed that you did test the perception of the teachers about AI. And at the same time, I think that one needs to probably test the perception of the teachers on the tasks that the huge list of the tasks that we have actually listed there. The reason I'm saying that is, it is surprisingly that the teachers, they don't think that reflection can be supported by tools that, let's say, learning analytics or artificial intelligence can provide. And that brings me to the point that probably if we are serious about teachers reskilling, we need to not only add one element of data literacy or artificial intelligence literacy into their existing curricula and perceptions, okay, but go back to the root and create the skill set that will revisit all their tasks to be supported by and perceived by technology-enhanced methods and tools. And I think that your this nice list of tasks that you have there, with reflection being the less interesting in terms of data support, it actually proves this case that otherwise, I think all these tools, they will not transform, and they will not use their transformative capacity, but they will just facilitate existing and in some cases mediocrity teaching that is already happening in European schools. So what's your point about that?
I definitely agree with you. I think you're perfectly right, and you put it in a very nice way. So we started that in order to see, we were thinking, okay, what is the next big thing? It's AI. So let's see how they feel about AI, especially, because they have this advanced, let's say, they're working in this advanced context in terms of ICT, and that's why we started from there. But I think that you're right. What they told us that they need support with practically shows that the whole skill set needs to be rethinked and updated, right? So I was definitely very surprised when they said that they don't need help with reflection. I'm thinking this might be because, I don't know, they are going through workshops. So teachers in Estonia, they go through workshops where they try, you know, for professional development. So it might be an impact that a lot of emphasis was put to self-reflection, and at some point they said, yeah, it's okay, that's enough. It might be just, you know, a wrong estimation of them. But I think this is definitely showing that the whole teacher's qualifications and skill set needs to be put on the table. It is kind of funny. I was reading this book, The Teaching Machines, and practically the author makes the argument that everybody says, you know, how education doesn't change. It's so slow to adapt changes and blah, blah, blah. But this is not true, because education changes every day. It is just that it doesn't change in ways that other fields change, or maybe the changes are not so visible. And I'm thinking these changes that we see in our educational system in practice, do we really take them into account when we design the teacher skill set, teachers education curricula, and professional development? So maybe there is also a mismatch there. So I think this is indeed a first step we took. And definitely, I would be more than happy to explore towards the direction that you pointed out.
Thank you.
All right, thank you. When I look to the clock, I know we have already got an hour. So Rita, it's up to you. If there is another question, probably you can decide if we have the time for a last question.
Yeah, I think we can have one last question. Any question on site? Any other questions? We don't have any questions outside. Yeah. So.
All right.
Yeah, I mean, any questions?
There's if there's someone in Teams, so please just raise the hand if you have a question. Maybe I can. I have a quick question. I think just about the time-based intervention that you mentioned at the very beginning in your talk, and I can imagine how this works when you have individuals learning, and how you can judge the time they probably need for an answer. But how does this relate to group learning? I'm curious, because I can't imagine that it's so easy to adapt this when you have a group of learners who are probably also using time for other things like discussion, like probably figuring out something. Just maybe a quick answer. How do you think, or how would you say does this relate?
Right. So you know, you take me back to the topic of my PhD thesis. Indeed, when we're talking about collaborative learning, you know, the level of complexity goes like over the roof. While I was doing for my PhD, I was doing learning analytics for collaborative learning, right? And what I was exploring is how we could model collaborative learning over time. I used time series there and so on. And what I saw was that the synchronicity of collaborating partners was an important ingredient in successful collaboration. I'm not talking about successful learning in terms of performance, right? But successful collaboration in terms of collaboration quality. And there I could see, you know, by the way they were working together on synchronous tasks, or the way they were using their chat tool, that being in sync with your collaborator was an important aspect of working well together. And I think this is something, you know, that common logic and practice, also our own experience, tells us. When our collaborator is in sync with us, we feel good about it. So I'm thinking that time-based interventions could help there to give nudges, you know, when for people who are not in sync, how you could sync, right? Reminders like, now it's a good time to ping your collaborator. Now it's a good time to do something about it, right? So this is how I envision that time-based interventions could work in collaborative settings.
Right. Yeah. Okay. Thank you very much. Thank you. So I think we are well over time now, but it was so interesting that I think everyone agrees it was worth the time we spent on this. So thank you very, very much again, Irene, that you've been with us today. And I hope we will meet soon because we are both geographically close. So thanks very much again. And thank you to everyone in the audience for listening.
Thank you very much.